And good afternoon, everyone. It's good to see a few people here. I learned most of my geology in this lecture theatre. And Sam Carey would stand up here, you had no problem hearing him at the back. And I'm just a bit sad to find that it's been decommissioned, and I'm sure I heard Sam turning in his grave down there. So, what the hell do you think you're doing in this place? I want to talk about Tasmania and where Tasmania comes from, where we've been over time. Tasmania is a wonderful place for geology. It's a wonderful place to be a geologist. And we have a really dramatic, interesting geological history in getting here. That's what I want to talk about today particularly. Some of you perhaps know my book, the Child of Gondwana book. That's been out there now for 3 years or so. And I've had a lot of good feedback on that, I have to say. So all of what I'm going to be talking about is in the book. So if you want to follow up, that's the best way to go. I do have 3 or 4 copies here today, if anyone doesn't have one but would like one straight away. So let's look at what happens and how the Earth works to begin with, the really big picture. And the first thing we have to know is that all of the continents on the Earth's surface are moving. This was a big argument back in Sam's day because nobody much believed that continents could move. They all seemed to be fixed. Now we know that they are all moving very, very slowly. The average rate of movement is 5 centimetres per year. The length of your finger per year, which is not much and is quite imperceptible to us, of course. We don't notice it. But over 1 million years or 100 million years, that's a lot of distance covered. So this is quite a good map to show you what's happening with the various tectonic plates. And the arrows indicate the direction of movement, and the length of the arrows indicates the amount of movement. So Australia over here is moving north at about 7 centimetres per year. And if you live to be 100, you're going to be 7 metres closer to the equator by the time you die. You probably won't notice that. The fastest movements are here in the Pacific, up to 18 centimetres a year. And some of them are really slow, less than 2 in places like this. So there are spreading ridges in the middles of the ocean where new crust is formed and the plates extend away from one another. And there are convergent places where the plates converge on one another. And when the plates converge, you typically either get continental collisions, which are really big things, or if it's oceanic crust, you'll get a subduction zone. And some of the oceanic crust is subducted down back into the mantle. So things recycle, basically. Sam Carey never really accepted the subduction idea. He called it American seduction because it hadn't been proved at that stage. And Sam was more convinced that actually the Earth was expanding because of that. Now I think it's pretty well established that subduction is a real thing and that the whole process of continents moving and being subducted means that the Earth's radius is basically stable. That's a really big picture. Why do continents move? That's a big question. And continents move because we have a hot core in the Earth. The Earth's fire is still going. And that heat that's coming out of the core is what's driving convection currents through the mantle, which are what is moving the continents around. I've simplified the process in my boiling billy analogy here. You've all seen a boiling billy or a pot on a stove with a hot spot under it, things floating on the top. What happens is that the heat is carried up through this area, whatever it is, and you get a convection current set up with the hot water going down, round, back in and up that way. And at the surface, that convecting fluid carries the continents or whatever is floating on the surface with it. And those lumps of porridge, I call them here, but in this analogy they could be continents, they tend to aggregate at wherever the convection cells go down. And that can be a stable orientation. But if you move the hot spot, and this is what's critical in terms of the Earth, if you move the hot spot over here, under this aggregation, what happens is that the lumps get pulled apart again. And the Earth is really a three-dimensional billy, a spherical billy. We have the heat source, which is the core, 5,000 degrees of hot iron in the centre with hot spots all around it. And these hot spots mean that hot material works its way up through the mantle to the surface, and as it moves along or separates, it carries the continents with it. It's a very simple process. And where the convection currents come down again, the continents will aggregate together. So they're pulled apart here and they're aggregating here. Now that can be stable, but the Earth's core is not stable. The hot spots and the hot places move around, and eventually the hot spots move, and if one of those hot spots turns out to be under a supercontinent, the supercontinent gets pulled apart again. And you get a different arrangement of the continents. It's a very simple process. But imagine the power of continents colliding with one another. They are so big, they're so slow moving, that when they collide, it's a pretty big deal. But that's the simple process of why continents move. When two continents collide, and a classic example is the Himalayan mountains, where India is colliding with Asia. Here comes India and here's Asia, say. What you normally will get is a big mountain range formed as the crust gets sort of doubled in thickness. The mountain range will push up to 8 kilometres, 8,000 metres is the height of the Himalayas. But underneath that is a great big root of continental material, which may go down to 30 kilometres. So there's a double thickness of crust here. There's quite a lot of heat generated in this central part in here. So you get metamorphic rocks which have been heated up and altered, involved in the process. There's a huge amount of folding, a huge amount of faulting carried on. The rocks are really squeezed and squished. And down in the hottest part of the depths here, some of the rocks actually melt and you get granite bodies formed. If you melt crustal rocks, it produces granite. That's all granite is, it's melted crustal rock of any size. So So you get granite bodies forming down here, and because they are fairly light, they make their way slowly up towards the surface, and they can be exposed after erosion. So this is called an orogenic belt, or an orogen, and typically after the mountain building process and the continental collision stops, the erosion and weathering, which is going on all the time, eventually lowers this, reduces it, weathers it away. The mountain ranges are taken away down to sea level. This happens multiple times on some continents, believe it or not. Mountain ranges are formed and then they're eroded away over maybe 100 million years. So it's a very long time factor involved. Tasmania has one such orogenic event in its geological history, in the Devonian, about halfway down. And I'll show you some of the evidence for that. So as we look back in time, we find that the continental arrangement on the Earth's surface has changed because of these changing hotspots in the core. And our oldest rocks, which are 1.4 billion years old, our Precambrian rocks, have been dated at 1.4 billion, which is not particularly old. It's old enough. Older than my grandfather, for instance. 1.4 billion, and back then, this was roughly what the continental arrangement was. This supercontinent is called Nuna, and here was where Proto-Tasmania was, up in this section between the old Antarctica and North America, or Laurentia as it's called. So Proto-Tasmania has characteristics of that part of North America and that part of Antarctica. So we can pretty well locate it in that position in between Laurentia and Antarctica about here. But this is 1400 million years ago. We were north of the equator and attached to North America. I'm glad we're not still there, really. So that was pulled apart when the hotspot moved and then rearranged. And this is Rodinia at about 900 million. Here's Proto-Tasmania still here between Antarctica and Laurentia. But Laurentia, or North America, is splitting away now, and it splits away and moves north into the northern part of the hemisphere, and it has its own evolution up there. We got rid of it, I think. But notice that Australia, the main part of mainland Australia, is still here and is still separate from Tasmania and from Antarctica this time. These orange belts are the orogenic belts, where continents come together and collide. You get a belt of mountains, folds, faults, metamorphic rocks, which are called orogens. And you get those around where the continents come together.
Can I ask a question?
Yes.
So does that mean that those ones on Australia and East Antarctica are from a previous collision, or is that where it will collide? The orogenic belts there?
That's a good question. Yes, that's probably where Australia and East Antarctica are colliding at this stage. Yeah. And finally, the next rearrangement, or the second next rearrangement, was Gondwana. And this is a fairly big agglomeration of continental fragments. These are the old cratons or shields made of old Precambrian rocks. There are a whole host of those around the world. And they're joined by these orogenic belts. This is South America here, obviously. This is Africa. India is in here, Antarctica, Australia, Tasmania, still part of Antarctica, still separate from Australia, from the mainland. We're different. And most of our Paleozoic rocks, in fact most of the rocks in the older part of Tasmania, were formed, deposited, when we were in this position in Gondwana. Part of this younger orogenic area, which also included the eastern part of Australia, a little bit of South Africa, and a fair bit of South America here, and part of Antarctica. So that's where most of our geological life.
Keep in that screen, please.
Gondwana lasted for 300 million years. That's a long time. I mean, the times in these things are so enormous that things can be stable. And the times are big and the rates of movement are small. But because the times are so big, the rates of movement add up. Gondwana started to break up roughly in the Jurassic. And this is a picture of Gondwana at about 180 million years ago when the dolerite's being intruded. The Jurassic dolerite is one of the most prominent parts of Tasmanian geology. You can see it on Mount Wellington if you look out the window. And what happened then was that there was a belt of dolerite intrusions, hundreds of millions of cubic kilometres of dolerite intruded at this stage into the crust from down in the mantle, indicating a pretty powerful hotspot. There's quite a lot of Jurassic dolerite and basalt in South Africa, the Drakensberg escarpment here, wonderful place, all through Antarctica to Tasmania here. There's a tiny bit of Jurassic basalt on Kangaroo Island and a tiny bit of Jurassic basalt at a place called Coleraine in Victoria. But there is none of the huge basalt sills intrusions that are so characteristic of Tasmania on mainland Australia. They don't have it. And that's one of the biggest of all reasons why Tasmania is different. Because we were here and we were affected by this great intrusion event of dolerite, but it didn't get to the mainland. Just in addition, if you've heard of Pangaea, the really big supercontinent, this is a picture of it here, Gondwana in the southern part and Malaysia in the northern part. So it's a big C-shaped supercontinent that must have occupied most of the Earth's surface. So things started spreading after the Jurassic, the hotspots working, the continents are being pulled apart. And at 40 million years ago, this was the situation. Here's Antarctica, pretty much stranded over the South Pole here. Africa's gone, South America's split away. India has been racing northwards at 20 centimetres a year, which is bolting speed for this. And it's crossed the equator already and is colliding with Asia at this stage. So they've all gone, except Australia still stuck to Antarctica here. And the reason it's still stuck is Tasmania. We're the sticking point. And this is where Tasmania is born. This is my diagram of the situation then. Here's Antarctica, there's mainland Australia. Here's the spreading ridge things are opening up like a zipper coming through Great Australian Bight here. Gets to here, just off the Otway area of Victoria, and it stalls. It should have kept going through that Bass Strait region. So why didn't it? I surmise, and I don't really know, but my suggestion is that there are two arms of granite which connect this bit of Tasmania to the mainland. One goes through the Furneaux Islands here, Deal Island, to the mainland, and this one through King Island here, like two great strong arms holding us. That may be the reason, but whatever the reason, what happened next, the zipper's still pulling open, the continents are still moving apart, you can't stop that. So what happens is that a series of great tear faults develop down the western side of Tasmania, and that whole corner of Antarctica gets pulled off. It slides north, so it's sliding horizontally on these big faults, and it's moving very slowly, so there was a long period when they were still connected, but moving away from one another. And this big wedge of crust is what contains Tasmania. There's another area of crust down here, which we'll see on an image in a minute, called the South Tasman Rise. That's continental material. And there's another area over here called the East Tasman Plateau. But because of the stretching, remember you're stretching the crust to pull them away, there's a whole host of stretching going on through this Bass Strait area. And what's happening is that several of these basins are forming like holes as the crust thins and stops. And Otway Basin over here, Bass Basin, the middle of Bass Strait, and the Gippsland Basin over to the east. Otway and Gippsland are mainly in Victorian territory, and they're the ones with the oil deposits. Bass Basin is entirely in Tasmanian territory. It didn't have any oil, probably still doesn't have it, but did have a gas deposit. More about that in a minute. This is something of what happens when you stretch that Tasmanian part of the crust. You get a whole host of pretty big faults happening where things drop down, and you get rift valleys, or graben as we call them. So here's the big Bass Basin here with all the faults. There's an extension of that up the Tamar Valley here called the Tamar Graben, and the Longford Basin here is another extension. There's one at Port Sorell. There's another one over here at Strawn called the Macquarie Harbour Graben. Just rift valleys that have dropped down and been filled up with younger sediments. There's a bit of it on the Derwent Valley, up around the middle part of the Derwent and down around Hobart here, Coal River. There's another one at Oyster Bay in between the Freycinet Peninsula and the mainland here. But the biggest one by far is Bass Basin, which we can't see. But we know a lot about it because there have been about 40 drill holes looking for oil, and all these little red bits are the drill holes. So we know quite a lot. John Davidson knows an awful lot about Bass Basin. The Yolla gas field is here, right in the middle here. Yolla gas field is quite valuable, but unfortunately what happened was that they piped the gas to Victoria, treated it there, and Tasmania buys it back via the gas pipeline. So we don't get much value out of owning that part of the territory. I just wanted to have another look at the Bass Basin here. At that stage, this is about 40, 50 million years ago, and I've reconstructed what it must have looked like from all the drill hole information. So it's all land. Tasmania developed here later on when sea level rises. But there's an awful lot of erosion of material carrying on. It's all being carried by rivers down into this hole that's sinking in as the Bass Basin. And as it sinks, it gets filled up with sediment. So it's like a sort of magic basin. The deeper it is, the more you can put into it. So it's never actually a hole in the ground. It's just a sinking basin which keeps getting filled up with sediment. And a huge amount of that sediment, perhaps most of it, is coming off Tasmania. And a lot of that would be dolerite, because dolerite is now covering a lot of northern Tasmania. There's quite a good example around Ben Lomond, which is roughly out here. If you look north of Ben Lomond, you see a whole series of little isolated dolerite mountains, Ben Nevis and several others. They're telling us that there was all dolerite there once, but that most of it has been carted out into Bass Basin. And what's left are just these little remnants that make the mountains. I did a rough calculation of how much material is in here. It's 10 kilometres deep. This thing has subsided 10 kilometres. That's a huge hole. And it's 350 k's long and about 150 wide. You multiply that out, you get a value of over 100,000 cubic kilometres. An enormous amount of material which had to be supplied, carried in by these rivers, of which the ancestral Tamar, draining all of this country in here, was probably the biggest. So the Bass Basin is a bit of a forgotten piece of geology, really, because we can't see it, but it's so important. Now, this is the image that's critical to understanding of all this. This was made from submarine surveys carried out by Geoscience Australia, based in Canberra. That's the federal geological group. And they just traversed all of this country, the sea, with sonar radar to get a detailed image of the submarine topography. And that tells us, see, here are the big fault scarps coming down this side and then roll the way down here. Those are the big tear faults that were there to move Tasmania away. This is the South Tasman Rise. It's sitting down there under a kilometre of ocean, so nobody ever sees it. But it's crustal material. There's samples have been dredged from it. It's clearly crustal material. There's another section over here called the East Tasman Plateau. It's about the same depth, except that it's got a big volcano sitting on top of it. And that volcano, or seamount, projects up to about 800 metres below sea level, still a fair way down. And these things here are other big seamounts off the southeast coast of Tasmania, other big volcanoes on the seafloor. How good is that, to be able to see all that from submarine surveys? That tells us where Tasmania came from. Good old BMR. So here we are now. This is the present situation. Here's Tasmania. Here's where we've come from. 3,500 kilometres away we are now. That's how far we've moved in the last 50 million years. moving at 5, 6, 7 centimetres per year. Just takes a lot of time to get anywhere. And those people that set off as voyagers to go back to Antarctica are sort of recreating that voyage that Tasmania itself has done. My daughter's been to Antarctica working. That's where they go, off down here. But that's where we come from. Hard to believe, no? The other thing about this map is that Antarctica now, having broken through this passage called the Drake Passage, South America here, seawater now rotates right around Antarctica, and it just gets colder and colder because it doesn't go to the pole, to the equator. It warmed up. It just sits down there going around, getting colder. And poor old Antarctica, stuck over the South Pole, it's covered in ice. I think we're better off where we are, don't you? So that's the story of where Tasmania came from. It's a pretty dramatic story, and the things to remember, I suppose, are that we're pretty different from the mainland. One of the biggest differences is obviously all of the dolerite that's here in Tasmania. Tasmania is probably the dolerite capital of the world in terms of how much we have per unit of area. There are literally hundreds of dolerite mountains here. I counted them up for the book. 500 and something. Mainland Australia doesn't have any. So we are different, and that's something of the reason that we're different. We've come via a different route. So that was the first part of my talk. How am I going for time? 5 minutes.
Yeah.
I'd like just to skip through a brief look at the main rock types that make up Tasmania from here on, so to get some idea of the diversity of rocks we've got. Our old Precambrian, Proterozoic rocks, the 1.4 billion year old things, are in most of southwest Tasmania. This is Federation Peak, perhaps the most iconic of our mountains. I've been to Federation Peak. This is Bechervaise Plateau on the side here. This is where the campers' camp is. To get to the top, you go up over this one down, and then that's the climbing face up there. Then you can come back down and continue around if you want to go on. I went there in 2001 with my son John guiding me. And standing on the top of Federation Peak is one of the great outdoor experiences in Tasmania. One of the great places. Surrounded by all those jagged quartzite peaks. Indeed. He's a bit of a poser, my son John, already. And this is what the quartzites look like. They have had a pretty hard life, really. These things started off as just horizontal sand layers on a shallow seafloor 1.4 billion years ago. They've been folded and squeezed and metamorphosed twice, perhaps maybe more than that. And you can imagine the forces involved in squeezing quartzite layers until they look like that. You can only do that when a continent collides with another continent. Coming up into the Cambrian, the younger rocks, these are the Mount Reed volcanics that I spent a fair deal of my career working on. This is a fairly old view now, looking down over the Mount Lyell mine area. This is the Iron Blow open cut, which is the first of the Mount Lyell mines to be developed. This is the West Lyell pit, which is now quite a lot bigger than that. And that's where the most recent mining was, but underground. So they take the ore out from underground and the top collapses a bit more. It's a huge hole there now, an absolutely huge hole. And this is Mount Owen over here of late Cambrian conglomerates. They're another one of the big units of Tasmanian geology. What happened there?
No, you keep going. It's up here.
Do we have to touch it again?
Yeah, touch the button.
Another view of the Mount Reed volcanics at Queenstown. These are the bare hills of Queenstown, so-called. They're not so bare now as they were 50 years ago. They're being slowly revegetated. Unfortunately, a lot of the revegetation is radiata pines, absolute weed. But they're still pretty colourful, and you'd still get a good sunset view from here looking over those multicoloured hills. The locals objected years ago when I think it was the company had an idea to actually go out and revegetate the hills. And the locals said, no, we like the hills bare as they are. And I don't blame them, because I do too. I think it has a real character to be able to see the colours of the rocks and the weathering materials. I don't want vegetation on. One of the old smelter chimneys here. So moving on to the conglomerates, which make up most of the big mountains over there, the West Coast Range Mountains, Mount Owen, Mount Lyell, Mount Sedgwick, Mount Jukes, Mount Murchison, all of those things are made of this Cambrian conglomerate. This is right on the top end of the Tyndall Range at Mount Tyndall. That's my old boss, Rod Hargraves. I'm sorry he didn't fall off there. Looking up to Mount Murchison here, Lake Plimsoll now covers this valley, a hydro lake. But this is Lake Selina, that's a natural lake. This is Glacier Valley, which I named, one of the names, with a big moraine along this side. But that's of interest because the next iconic walk you may have heard of is going to be through the Tyndall Range. And the early part of that walk will come in about here and come up this valley for some distance before climbing up the eastern side there. So that will be part of the next iconic walk if it happens. These are the conglomerates. They're just pebble river gravels, really. A huge mass of river gravels made of quartzite pebbles from those old quartzites we saw a minute ago, brought out by huge rivers on great big alluvial fans from a range of quartzite mountains. Absolutely bare because there was no land vegetation at this stage, so nothing to hold the gravels together. And up to 2 kilometres thickness of these things at Mount Lyell itself, which is a huge thickness. But pretty nice, easy rocks to work with, not like those horrible Mount Reed volcanics, which are full of cryptic textures and stuff. Thanks, Jocelyn. And moving up the geological column to the Devonian granites. You all know what granite looks like. They're an important part of the story, particularly on Freycinet and those places. But But there's one thing that happened within our Paleozoic sequence which is important. I said we had one orogenic movement in Tasmania, the Tabarabaran orogeny we call it. It happened in the middle of the Devonian, and something happened somewhere outside Tasmania. There was a collision and all of our old rocks were folded and squeezed and to some extent metamorphosed then. Quite an important event in our history. And you can see the results of this best if you take a boat and go out around the other side of Maria Island. Because out there, you see these old folded Paleozoic rocks. These are Silurian Devonian slates and so on. Eroded off and covered by horizontal Permian rocks. And that's the surface there. This is one of the best exposures of an unconformity in the world, in my view. Because what happens with orogenic mountain belts is they get eroded after they stop rising. The erosion takes over and they can be eroded right back to sea level. That's what happened here. These are the roots of those mountains, eroded back to sea level, then covered by these horizontal marine Permian sediments. Absolute classic geology on Maria Island. This is another view of that unconformity. You can see the horizontal Permian here. But in this case, we have the granite. You can see intruding these old slates. Here's a granite intrusion coming through here and over here. So this just fits the granite into the story pretty nicely as well. It was part of that orogeny and part of the erosion which lowered the sediments to sea level, and then the Permian over the top. All geology students should go to Maria Island. So those Permian horizontal sediments, you see them around Hobart. They're probably the most abundant rock type around Hobart. You see them around the foothills of Mount Wellington, Ferntree. You see them down on the foreshore, on the shore platforms, at Taroona over on the eastern shore. They make beautiful shore platforms. Quite often you'll find dropstone pebbles scattered through them, where glaciers have melted in the sea and dropped their load of pebbles. Permian mudstone, very common around Hobart. And above that again, the Triassic sandstone, which is what many of our old sandstone buildings are made of, a really nice rock, nice golden yellow colour. These are all non-marine, these are river sediments, particularly lake sediments, some of them, and really nice material. This is down at Conningham, down the channel. Those are my grandsons behaving themselves for once, to give a scale. And then there's the dolerite. Just going back to that diagram of where we were when the dolerite was intruded. Southeastern tip of Antarctica. We caught the dolerite, but the mainland didn't.
Can I ask a question about the dolerite? Was it intruded in one spot, or was it along a rift? Did they have a place where it was intruded?
I'll go back to the map if I can. It's probably an early kind of cracking along this edge of Antarctica and Tasmania. Not sure how that fits with the South African section, but it came up in multiple places, lots and lots of different places. In a number of places it actually got to the surface and erupted as basalts. So a lot of the Jurassic igneous activity is in the form of basalt, surface lava flow. That's what you see in South Africa here too. But we don't have very much of that in Tasmania. What we have is this columnar jointed thick sill sheets of diorite, making the tops of our mountains everywhere. This is the road up to ski field at Ben Lomond. Trying to think of the name of it.
Jacob's Ladder.
Pardon?
Jacob's Ladder.
Jacob's Ladder, thank you. This is Jacob's Ladder. Pretty hairy place. I've known people come drive up to the bottom of this, look up and then turn around and go home again. This leaning rock here was considered to be a hazard for a long time. They finally got around a couple of years ago to blasting it off. And they closed the road, obviously. They got in here and put a fair amount of explosive material behind it. Blew the thing off, it came tumbling down onto the road here and the window and down here somewhere, just to get it out of the way. Diorite's a great rock, but it's pretty expensive stuff to build roads through, or tunnel through, or any of those engineering things. But counteracting that is its value as a maker of mountains and grand scenery. And coastlines. This is Cape Pillar down on Tasman Peninsula, and there the diorite is right down at sea level, and you get these wonderful cliffs of columnar jointed diorite. The columnar jointing happens because it's a hot rock when it's intruded. As it cools, and this happens with all igneous rocks really, as it cools it cracks, contracts, cracks, and it cracks into that interlocking hexagonal pattern, which is so common in nature. And as the cooling goes down through the sill, the columns go down through the sill as well, and eventually they'll go right through to the bottom. So columnar joints, although it makes it look as though the diorite has some sort of vertical structure, in fact it's a horizontal sill with jointing. Younger still in the tertiary or the Cenozoic are our basalts, mainly on the northwest coast. You see them. This is the famous nut at Stanley. I was on top of the nut at Easter with my wife. It's a really nice walk up there. The nut is the nearest thing we have to a volcano left in Tasmania. It's 12 million years old. And when you reconstruct it, this is what you get really. An original volcano wrapped around the nut, made of ash and thin lava flows and so on. And a huge amount of basalt was erupted into the core, the crater of this volcano, and formed a lava lake, as we call it. And that lake has consolidated into this big mass of basalt. Over the 12 million years since, all of these sides have been eroded away. There's still a little bit of the ashy material on the seashore here. But the big mass of basalt is still there. So it's a remnant volcano. And unfortunately, we don't have any young volcanoes which still preserve the volcanic shape. Not like those nice things they have in Western Victoria, Mount Gambier and so on, which are only a couple of million years old at most. And the basalt produces the most wonderful red soils. I was brought up on a basalt farm, a bit like this. And they're the sort of showpiece of our agricultural industry. They're so fertile and they're so deep. You can find cuttings through this basalt with 5 metres of this red soil. Unbelievable stuff, unbelievably fertile. But to get to this stage, the basalt country went through this stage. All of that basalt country in the northwest was covered by tall, dense forest back in the early 1800s. And how they managed to clear that was firstly by ring barking the big trees, 100 of these per acre in many places. That's a lot of work to get rid of them. You can see they've been ring barked. You kill the tree so it doesn't grow anymore. You clear out the undergrowth underneath, and then you can plant your potatoes or whatever. Get something back and deal with the trees when you get more time. That's what they did. If you travelled through the northwest coast in about the 1880s, you would have seen mile after mile after mile of dead ring-barked trees as the settlers were clearing their land. It took ages and ages. Quite a different story to the Midlands grazing properties, which people could simply go to, let their sheep out of the truck or whatever, and they were ready to go. There was grass there, there were clearings there were natural paddocks. They didn't really have to do much at all. But on the northwest coast, where the really good soils are, this is what you had to go through first. Not much sign of it now. All of these original forests are gone, but that's how it was. And there are sedimentary rocks also associated with these tertiary Cenozoic basalts in places. This is Fossil Bluff at Wynyard, and you've got these near-shore sandstone deposits. Here, sitting on the Permian Wynyard Tillite, right, so that old Permian Tillite, there's quite a time gap here on this surface. The Tillite's about 300 million years old. These sandstones are about 25 million, I think, so there's a hell of a time gap represented here with just erosion. It's not an unconformity because there's no discordance in the angles. They're both parallel still, but there's a disconformity and a considerable time gap there. That's a good place for students to collect fossils. Look at some of those sandstones, and they're absolutely packed with shells and material. And it's interesting because when you look at it, you think, gosh, that's not old at all, because you sort of identify the shells. You've seen the shells before, they haven't really changed much. I was up there as a second year student adding to my fossil collection, which you had to have in those days. And we found some little black bones sticking out of the side of one of these sandstone boulders. I brought it back to the university here, and Max Banks encouraged me to clean it up, which I did over weeks with a dentist drill. It turned out to be a flathead skull, virtually identical to the modern flathead. Virtually identical. So flatheads haven't changed much in 25 million years.
Price has gone up.
Price has gone up. Yeah. And the last stage in our history is another important one. It's the Pleistocene Ice Age, which has been for about the last 2 million years. And we've had a number of sessions of ice age, and then interglacial warmer period, and then back to a glacial period. That's probably happened 20 or so times, which is hard to believe, really. But the glacial stages went for about 100,000 years, and the interglacial warm stages, which is what we're in now, go for about 10,000, maybe 20,000. So we've been in it now for 10,000. Theoretically, we should perhaps be heading back into a glacial period. But I fear with man's mucking around with the earth, we might never quite make it back to a glacial period. So this is Dove Lake and Lake Wilkes here, which is one of our classical glacial valleys. And as I say, ice has been down this valley multiple times, probably 20 odd times over the last 2 million years. And this is an aerial view just to give an indication of how much material the ice has taken away. Here's Cradle Mountain, and it's just a sliver of the dolerite that's still there. And Barn Bluff is another little remnant of the dolerite. But all the rest of this country was also covered with dolerite. So it's all been stripped away, mainly by the ice, I think, in the last ice age, and carried away, dumped in the moraines and in the rivers and so on. Just an indication that erosion is a very important process in our geological history. We always think about sedimentation making things, but erosion taking things away can be just as important. And the very last phase, which we're still in, is called the Holocene interglacial warm period. So we're in an interglacial warm period now. We have been for the last 10,000 years. All the ice, not all the ice, most of the ice has melted. Sea level has risen by maybe 120 metres. 120 metres. And it's flooded all of the river valleys around the state. And this is on Mount Rugby, looking down the Bathurst Channel at Port Davey. And that's a classical drowned river valley, which is what's happened to all of our river valleys, really. And what you see are little islands, which are the tops of the original hills, still just sticking out of the water. But we're in a warm period, you'll be pleased to know. And it may last for considerably longer than the last warm period. I think that's it. Yes.
Let me just turn the lights on.
Let me just finalise the important points. Tasmania's had a pretty dramatic geological history, coming from a piece of Antarctica, different from mainland Australia. We're really a piece of Antarctica. We know that because of all the dolerite that's here. And you see heaps of dolerite in Antarctica. You don't see any on mainland Australia. So we are different in that sense. We have a very strong geological connection to Antarctica. And I'm always a bit surprised that that doesn't come out in our politics. Yeah, that's it. Thank you all.
I'm going to